One of the last things we'll finish up this series with is talking about the central limit theorem. This is, again, another stepping stone for the remainder of the course because at the end of the day, if you took nothing else out of what we've talked about so far, it's that we have to use sampling as a technique to acquire data about a population since it's generally impractical to be able to survey an entire population. So the central limit theorem tells us as your sample size gets infinitely big, so as sample gets big, right? And I know that doesn't sound very mathematical, but that's how it's said. As the sample size gets big, our sample becomes approximately normal. Now, why is this so important to us? Well, this is really important because if you took a sample that's not approximately normal, there's practically nothing you can do with it. We've talked before about the fact that really small samples can be incredibly skewed. So what do you have to ask yourself in order to use the central limit theorem, and I'll talk about how that actually gets calculated in a moment, is if your original population is normally distributed, well, if you know that the population is normally distributed, you're good to go. If the population is not necessarily normally distributed, but your sample size is greater than 30, then again, we're good to go. So this is what we consider to be big. So we have to check these things. However, on the other side of things, if your population is not approximately normal or normally distributed, and I forgot to mention here that this means approximately normal. Now, on the other hand, if it's not greater than 30, so we have a really small sample, then we have to be careful. For this level of statistics course, there's nothing we can do about this. If your data is skewed, it might actually follow a chi-square distribution or something else. If you were to take a Stat 2 class, you'll focus more on what can happen here. For us, we're just going to look at cases where we're coming from a normal population and when our data is either approximately normal or if the sample is greater than 30. The only way we can deal with less than 30 is if they tell us, so they must tell us that we have approximately normal. So you might have a small sample, but they have to say approximately normal. Let's look at an example of this. According to an IRS study, it takes 330 minutes for taxpayers to prepare, copy, and e-file a 1040 tax form. The distribution is approximately normal with a standard deviation of 80 minutes. A consumer watchdog agency randomly selects a sample of 40 taxpayers. Right off the bat, they tell us the IRS is saying it takes 330 minutes. So that's a population mean. Some government body is telling us what it is. The distribution is approximately normal, so it doesn't matter from here what that sample size is. As soon as they said approximately normal, we're okay to use the normal distribution. We have a standard deviation of 80. They randomly select a sample of 40 tax returns, so n equals 40. What's the probability that the sample mean is greater than 320 minutes? So we're looking for x greater than 320. Well, the central limit theorem allows us to use a spin-off of the z-score formula. What does that look like? Let's see. Well, if 330 is here, 320 is over here, and we're looking for greater than, which is off to the right. Now, unlike before, let's go back to our formula sheet here. If you remember from our sampling distributions of sample means, we talked about what it meant to have to scale our standard deviation. We're no longer dealing with that standard deviation because that only works for the population. But here we have a sample. So we're going to use our sampling distribution formula. You'll notice the only difference from our regular z-score to our sampling distribution is that we're dividing by that square root of n at the bottom. So we're using the scaled standard deviation value. So using that formula, we have z equals 320 minus 330 divided by 80 over the square root of 40. Be very careful how you type this in your calculator. If you do this all at once, you need parentheses around the numerator and also around the denominator. Do not, under any circumstance, round the denominator. I would say get used to typing this in all at once. This gives us a z-score of negative 0.79. Now, if our z-score is negative 0.79, go over to our chart, we get an area of 0.2148. However, that's stuff on the left. We want the area on the right, so we use the complement rule. 1 minus 0.2148 is 0.7852, which is the area we were looking for. In other words, the probability that the sample mean is greater than 320 is 0.7852. You'll notice also, if you look closely, they say, what's the probability of the sample mean? So they're telling us if you were to take a sample, what's the probability that the mean has a certain property? Unlike earlier when they were saying, hey, what's the probability that you just get some number, some specific number they gave us? This is very different because they're specifying if you were to take a sample. Let's try another. What's the probability the sample mean is between 300 and 320? If you recall from when we first talked about how these things work, right, so we shade between them. If you have two x values, let's call this x1 and x2, we have to go ahead and find two z-scores. So z1 equals 300 minus 330 over 80 over the square root of 40, which gives us negative 2.37. This 320 we found the z-score of above, so I'm just going to copy that down. No need to, again, reinvent the wheel. And that was negative 0.79 with an area of 0.2148. The area for negative 2.37, 2.3 over to 7 is 0.0089. And one last thing, last step, when you're looking for the area between, you always subtract the bigger minus the smaller. So 0.2148 minus 0.0089, and that gives us 0.2059. So the probability that the sample mean is between 300 and 320 minutes is 0.2059. There's nothing too crazy different about calculating these values. They're really done in the same way that you calculate it if you're not dealing with a sample, only now we have to change the formula a little bit. So go ahead and practice these and let me know if you have any questions.